Welcome to Ask and Learn.
The object's mass is given as 280 grams, and its position function is given as 5t cubed minus 8t squared minus 44. So that's the position function. And we need to calculate the net rate of work done. So rate of work, which is basically power, and power is equals to force times velocity, and force is equals to mass into acceleration times velocity. So first of all, we need to find out its velocity function. So velocity function is dx by dt. So we'll derive the position function first, which is equals to 15t squared minus 16t. So that's the velocity function. Sorry, the position function here was actually 44t. So therefore, the velocity function is going to be 44 in the end here. So velocity function is 15t squared minus 16t minus 44. Then we need to find out the acceleration instantaneous function. A is equals to dv by dt. And acceleration function, if we derive this with respect to t, we'll get 30t minus 16. Now we can start finding out the rate of the work done, which is power, is equals to MAV. That should be equals to 0.28 times, and we'll plug in this function here, which is the velocity function. So the acceleration also is there. So 0.28 is the mass in kilograms of this object, and then we have A times V. So we plug in the equation. The acceleration function is this, and we just plug in at the value of 2 seconds. So it's 30 times 2 minus 16. That's the acceleration at 2 seconds, and the velocity at 2 seconds is given by 15 times 2 squared minus 16 times 2 and minus 44. So that's the power instantaneous, at this 2 seconds. If you solve that, you'll be equals to minus 197.1 watts. So that's the first part of the problem. Then for the B part, it says at 4 seconds. So again, power is equals to MAV, and if you just plug in the same equation there with the acceleration and velocity function, and we plug in A at t is equal to 4 seconds and t is equal to 4 seconds for velocity, we should get 3844 watts. So that should be pretty simple. Then the third part of the problem, it says that what is the average net power output? So average net power input. So average net power is the work done divided by the elapsed time. And if you use the work energy theorem, the work done is equals to the change of kinetic energy. So we see that when time is equals to 0, then the object is moving at initial velocity of 44 meter per second. Then if time is equals to 2 seconds, then the velocity instantaneous at that point is 15 times 2 squared minus 16 into 2. This is 16 times 2. This is times minus 44. So that should give you negative 16 meters per second is the velocity at 2 seconds. So now we come to the A part of the problem. We have the power average from 0 to 2 seconds is equals to the change of kinetic energy during that duration divided by time. Change of kinetic energy are the same units of work. So which is equals to half m vf squared minus vi squared divided by delta t. And that should be equals to half times 0.28, and the final velocity was negative 16 squared minus we have negative 44 squared divided by 2. If you solve that, you will get negative 120 watts. So that is the average power between 0 and 2 seconds. And now we can also calculate the average power from 2 to 4 seconds, which is equals to the change of kinetic energy during this time, which is delta K by delta T. Again, it is equals to half m Vf squared minus Vi squared divided by delta T during this zone. And that is just plugging in the values now. Half m is 0.28. The final velocity is 132 at 4 seconds squared minus the velocity is 16, negative 16 here, squared divided by 2. If you solve that, you will get 1200 watts. So note that we also used the velocity here at 4 seconds as equals to 132 meters per second. You can find this velocity by plugging in the value of time in the velocity function. So therefore, the average power which is generated between 2 to 4 seconds is equals to, as you can see, 1200 watts.